All right, so in this section 3.3, we're going to be kind of extending this stuff that we did with the vertices of the triangle. So we're still going to be graphing inequalities. We're going to be figuring out where the vertices are, and then we're going to be using them to find minimums and maximums of different functions that we're going to be dealing with. So the first thing we need to introduce when we're finding max and min is what a feasible region represents. And a feasible region is basically the vertices that we were looking for before. So we could have two different regions, and I'm going to give just a quick sketch. So let's say we had something like what we saw yesterday, where you've got lines that intersect like this, and you end up with a triangle that's totally closed off. We call this feasible region a bounded region, so it's totally enclosed on all sides. So this ends up being a bounded region, meaning, like I said, it's enclosed. It's blocked off on every side. This one's going to have 3 vertices. Potentially they could have 4, depending on what your inequalities were that you were given. We could also have something like this, where maybe you've got, a line that goes right here, but perhaps these 2 lines are parallel to each other, something like that. So you would have a vertex here, but then you wouldn't have anything else. So this would be unbounded because it would go down forever in this direction. So this is an unbounded region. Okay, so this, let me shade this in here, like this whole region is just the triangle that gets blocked off. This region right here would just go forever, kind of down into the left. So that would be unbounded because it's open. It can go on forever in one direction. Okay, so just those vocabulary words to keep in mind, and we're going to move on to our first example here. So this is really similar to what we did in the second video of 3.2. We're going to be graphing, starting with these 3 equations, and then I will work into how that applies to everything. So graph the system of inequalities. That is what we are starting with first. So this one, remember when it's just an x and there's no y, that makes it a vertical line. So on my x-axis, I'm going to go over to 5. It's right there. This is a less than or equal to, so I know that it's going to be a solid line, just a vertical line where the x value is always 5. And then x values that are less than 5 are the ones that are off to the left. So it's almost like shading in a number line. So you go off to the left here. Every single value that I'm shading, the x-coordinate is something smaller than 5. Okay, and then the ones on the line are the ones that are equal to 5. So starting with that one, second one, y is less than or equal to 4. So if it's just y and there's no x, that's a horizontal line. So I go up to a y value of 4, that's right here. And then I'm going to extend that line to something that looks horizontal. So everything on this line, the y value is always 4, no matter what my x value is. And then less than 4 includes 3, 2, 1, 0. We go below that line. So shade everything below that line. So everything that I'm shading right now has a y value that's something smaller than 4. And then if you're on the line, the y value is equal to 4. So here's the overlap so far, is in this region right here. So all these x values are smaller than 5. All these y values are smaller than 4. And then I'm going to graph this line right here. So let's add a little bit of detail here. For my x-intercepts, you plug in 0 for y. So I end up with just x equals 2. For my y-intercept, you plug in 0 for x, like this, and so you get 2 for the y-intercept as well. So starting at the origin, let's plot a y-intercept of 2 and an x-intercept of 2. And then we're going to connect the dots, but remember from the end of 3.2, we need to be super, super precise. So here we go down 2 to the right 2. So connect those, and now if you notice, it's going to go through every single corner. So I can go through the next corner, the next one, the next one. Super accurate because we need to know that this is the exact intersection point. And then same thing in the other direction, right through the corners, right there, so you know that that's the intersection point. Okay, so it was important to be super accurate so that you can see the intersection point of this closed off region. So this region in the middle is what we're looking for. Okay, this one ended up being bounded, if we use our vocabulary from the previous page. So it's a bounded triangle, which means we have 3 vertices, and these vertices that we practiced getting the other day, we're going to write those down right now. So this one right here, this is on the line x equals 5. So let's make a list. These are my vertices. So I have, this is 5, and then I'm down 3 units. So 5, negative 3. This one up here, this is also on 5, and then I'm up at 4. And then this one right here, I've got -2 on the x-axis, and then I'm up at 4. So what I'm going to do with this function over here, so we've seen notation like f of x, and that's like y is a function of x. This function right here is a function of both x and y. So what we're trying to do is we're trying to see how we could get the maximum and minimum values of this function. So we kind of went through, we graphed, here it is, we found the coordinates of the vertices, here they are, and the final thing we're doing is finding the maximum and minimum values of the function. So we're going to take these vertices that we got, and we're going to plug them into this equation right here, okay? So we can almost make like a little table for these values. So we are going to start with our coordinate point, x, y, and then we're going to plug it into the function, and the function is 3x minus 2y. Okay, so it's kind of like making a little table. Similar to what we did before, except now we're dealing with 2 variables at a time. So my first coordinate point is 5, -3. So I'm going to plug that into this equation right here. So 3, I'm going to replace the x with the 5, minus 2, and then replace the y with -3. So this is 15 minus -6. So 15 plus 6 gives me 21. That's my first value. I'm going to plug in my second coordinate point now. That's 5, 4. So same thing I just did. Replace the x with a 5, and then this time replace the y with a 4. So this is 15 minus 8, and 15 minus 8 gives me 7. And then my third and final vertex, I'm going to plug this in now. So 3, now the x is being replaced with a -2, minus 2, and the y gets replaced with a 4. So this is -6 minus 8. So -6 minus 8 is -14. Okay, so those are my 3 values. Finally, what I'm doing is I want the maximum value and the minimum value. Okay, so here's how we are going to write that. So you're going to say maximum value, and we just look at this table. The largest value we found was 21. The max value is 21 at 5, -3. The minimum value, the smallest we have here was -14. -14, and that happened at -2, 4. Okay, so the reason that we can say the maximum and minimum values are occurring at these vertices is because these are the farthest edges of our shaded region. If I plug something in the middle here, I'm not going to get a max or a min, I'm just going to get a random value. So since they're almost like the endpoints of our shaded region, so they have the potential to give us either the largest or smallest value. Okay, so let's do a second example here. So first step, graph the system of inequalities. So we can start with this one. So let's label these 1, 2, 3. So equation 1, let's start with x and y-intercepts. So x-intercepts cover up the y, divide by -1, so I get -2. My y-intercepts cover up the x, divide by 2, and I get 1. Okay, so this one I've got an x-intercept of -2 and a y-intercept of 1. So follow the same pattern, up 1 to the right 2, just keep that pattern going. And you can take it off to the other side too. Okay, we need to be super accurate so we get the right vertices. Okay, it's got the or equal to, so we know it's going to be a solid line. And then we'll worry about all the testing in just a minute. Okay, second one. X-intercept and y-intercept, because it's in standard form. So cover up the y, my x-intercept is 4. Y-intercepts, cover up the x, divide by the -2, and I get -2. So 4 for my x-intercepts, -2 for my y-intercepts. So I want to keep this pattern going. I could go up 2 to the right 4. I could cut it in half and go up 1 to the right 2. So let's keep that pattern going. It's like this. Now notice, these lines end up parallel to each other. So since I've got 2 parallel lines, I'm actually going to end up having an unbounded region. So I'm going to get to see one example of each. So these 2 are never going to intersect each other. So my region will end up unbounded. So let's look at this third one. So the third one, x-intercepts, I plug in 0 for y, and I end up with -2. And my y-intercept, I plug in 0 for x, and I also end up with -2. Okay, so Here and here are my exact intersection points. That's nice, because here's my x-intercept of -2, and here's my y-intercept of -2. So I go down 2 to the right 2, down 2 to the right 2, keep that pattern going, and I can also go up and to the left to reverse it. Okay, so connect the dots here, and I can already see where my intersection points are going to be. Since I'm unbounded, these are actually going to be my only vertices. I don't have any more over here because these two will never intersect. So my vertices, I only have 2 of them. This is right on the y-axis. This is 0, -2. And this one's right on the x-axis. This is -2, 0. Okay, so I've got this unbounded region. Let's look really quickly at where it ends up shaded. Okay, so this piece right here, I can start with that. If I plug in 0, 0, is 0 less than 2? Yes, it is. So for this first one, I shade the region that includes a 0. So it's going to go all the way under here. For this next one, is 0 less than 4? Yes, it is. So I would end up shading underneath for this one. All right, and then this one right here is 0 greater than, oops, I'm sorry. Okay, this one I did wrong. I'm sorry. We want to shade what contains 0, 0. So it should actually be this right here. Okay, ignore that shaded region. So far I have everything in between these two lines, but I'm going to overlap and get the darker region. So now here is 0 greater than -2. Yes, it is. So in comparison to this line, we shade towards where the 0, 0 is. So we end up shading this over here. And so the overlap ends up being in between the 2 parallel lines and to the right of that other third line. Okay, so this is my unbounded region. It's bounded by these 2 vertices, but it's unbounded to the right. So I'm going to do the same thing that I did up here, get my min and max values by plugging into this function of x and y. Okay, so I can make a table. I start with coordinate points, and I plug those coordinate points into this function right here. Okay, so my first coordinate point is 0, -2, and my second is -2, 0. So here, plug in 0 for x, plus, and then plug in 2, -2 for y. So this is 0 plus -6, so I end up with -6. And then this one, plug in the -2 plus 3 times 0. So this is -4 plus 0. So that is -4. So I am going to, whoops, that was off the screen. I am going to write down my min and max values. So my max value, just ignore my line here. The larger of the 2 is -4, so that's my max value. And that occurred at the point -2, 0. So it's very important to write both the value and where it occurred. And then my minimum value is -6. That's the lower of the 2, and that occurred at 0, -2. Okay, so in the next video we're going to take a step further, but we've got this practice for now, just finding the actual vertices of our bounded or unbounded regions.